Hi everyone, this is Joey Berkowitz, and I'm going to talk to you about some uplift modeling evaluation, building off of what we put together last week for milestone 3. So to start off, I want to talk about a mistake I made during the last milestone. So if you notice to the right, this is the cumulative gains chart that I presented last week as part of my model evaluation for my random forest regressor. The model, as was pointed out, was considerably better performing than anything that we presented as part of the two model approach, which we thought was originally due to the new transformed outcome approach that we were going to try out. But actually, I noticed that the model was performing so much better because I was including two variables that should not be included as independent variables within my model. So I mistakenly included the exposure and the visit feature within the model. The visit feature is included in our data set as a different target variable if we want to build a model towards that rather than the conversion. And then the exposure variable is whether or not a user in our data set was served an ad or not. And we're not going to be able to know whether or not a user was served an ad when building an uplift model. That's sort of like the action that you would take from building an uplift model. So neither of those should be included in building any of the models that for uplift modeling. And so this week I started building my random forest model again without those variables, and you'll see the results of that later on, but definitely wanted to point that out as we progress throughout the project. Moving forward, I want to talk about the information or the net information value for the data set that we had. So the net information value is really a feature by feature calculation of how much a given feature is sort of present in the positive or negative occurrence of the target variable. So basically, how often does a given feature, basically what is the presence of that feature when the target variable is 1 versus 0? And that's sort of the easy way to think about it when it comes to binary classification. But applied to uplift modeling, we're really looking for the net information value. So it's really just an extension of that information value applied to uplift modeling. So it really compares for any given feature, it compares the log odds of the conversion being 1 within the treatment group when that feature is present or a certain value, and the log odds of that conversion being 1 in the control group for any given feature, and it sort of subtracts the control log odds from the treatment log odds and gives us that net information value. So looking at the plot to the right, only 6 of the 12 features that we have available actually had a positive net information value. So as I move forward, I actually tested whether or not using just those 6 features was going to give us a more parsimonious and more effective model. Unfortunately, it didn't. The model performed significantly worse when using just those features. So I stuck with using all 12 of our features when building the uplift model. And so I continued using randomized search cross-validation for my random forest regressor with all 12 of those features, using 10% of our data set with threefold cross-validation and 10 different iterations of hyperparameters. We were really tuning towards the max depth and the minimum sample split of my random forest regressor. and I really attempted to tune the model with the number of estimators as a hyperparameter, because it's, the number of trees and the random forest is really important, but unfortunately it really hampered the performance and the speed of the model that I was building, given the size of the sample that we were working with. So I decided to keep that steady at 100 through the entire model building process. And the training time for my model was, or my cross-validation was around 90 minutes for those 30 different folds. And the best performing features were actually the maximum depth of 69 and the minimum sample split of 139. So that's what I used for my final model, which you'll see here. I fit those on the data set, and we yielded a cumulative gains chart with the blue bar to the right. I wanted to include in the gains chart what the model would look like if we fit the model with noisy training data. And so you can see that it really doesn't perform much better than random selection with that noisy data. And our final model yielded a Q1 score of 0.1495. So comparing our model to the practical maximum and the theoretical max, random selection, and a model without targeting sleeping dogs, you can see that the model does perform consistently better than random targeting throughout all deciles of our users. In actuality, what this means is that we could hypothetically utilize a model like this for being able to segment our population for those who are actually going to be persuadable, and target those users who would exhibit the highest uplift between for our conversion and yield better marketing ROI for any given client. Things that we definitely want to consider when we build our final model is that we are going to train our model on all 25 million rows of the data set that we have available. But in practice, performance speed is going to be very important, given that this is geared toward display advertising. So digital display advertising happens in real-time bidding environment where there's programs and platforms that allow bidding and ads to be served within milliseconds of a page loading. And if we're going to layer a model which targets users most effectively using uplift, that model needs to be able to perform quickly. An alternative would be to sort of train a model at the start of a given ad campaign and update the model at given intervals based on new data that we have available. So it's not processing all that data at once, and we can sort of iterate over and over on the model, within given intervals. Another thing to consider in sort of a real-world application of something like this would be introducing something called a scoring cutoff. So if you go back to the model, we do have the ability to break out the percentage of our target customers to the highest 60% likely to convert, let's say, or because we are segmenting our population into deciles. So what that would mean is that we could potentially weigh the cost of serving ads to a persuadable customer versus what the cost of that ad would look like. So to sort of maximize the ROI, do we only want to target do we want to set up a cutoff of we only want to target 60% of our highest probability of conversion users? So to really find that cutoff that allows us to maximize the potential gains versus the cost of serving those users ads. And then a last thing to consider, and something that you can run into a lot is in the advertising world, is that does the audience, or does the client that you're working with really want to sacrifice a portion of their potential customer base to test on a control group? So you have to consider the size of the target audience that you are potentially serving ads to, whether or not the client wants to sacrifice a portion of that to building a control group and building a model like this is really dependent on the client. And it's easy to work with anonymized data and artificial data that we have, or not artificial, but anonymized and really not real world data that we have here to build a model like this. But in practice, it's going to be a lot more difficult when working with a real live client and real money at stake. So those are things that we're definitely going to consider moving forward. And then eventually, as we train our data on the full model, we will have some definitive conclusions as to which approach is best to take. Thank you.